All right, so in the previous videos, we talked about how we can graph a rational function using transformations, just the typical transformation rules using the parent graph. In these videos, we want to talk about how we can do graph rational functions where transformations are not going to be so simple. So we get more complicated numerator and denominator expressions, and we have to use more algebraic techniques than just transformations. So let's get right to it here. It says sketching graphs of rational functions. Here's our process. We have kind of 5 steps, and the 5th step is sort of an optional as needed step. So really the key here for graphing rational functions is always going to be find the intercepts and find the asymptotes. So if I were to ask you how do we graph rational functions, I would hope for your answer to be, in short, intercepts and asymptotes. Okay, so we can all say together, how do we graph rational functions? And you'll say intercepts and asymptotes. One more time together. How do we graph rational functions? Intercepts and asymptotes. Okay, and once we've got those features, we'll be able to sketch those features, and then we can plot any extra points that we need to in order to fill in the spaces. But we know the parent graph looks like this, right? And so most of our rational functions are going to look something like that. We will see that if we have multiple vertical asymptotes, we could end up getting something like this, where we have 3 pieces of our graph, okay, and a few other varieties as well. So we'll look at a few different examples here, but they're all going to look something like this-ish. Okay, so let's go ahead and start graphing this one here. If f of x we're given as 2x plus 6, or excuse me, 2x minus 6 divided by x plus 3. So first thing we want to do is find our x-intercepts. We remind ourselves up here that to find our x-intercept, we set the function equal to 0. So for x-intercept, I'm going to set the function equal to 0. And I just need to solve for x. Now, the only way that a fraction can be equal to 0 is if the numerator is equal to 0. So you also might hear me say a lot that when we're finding x-intercepts, really all we need to do is set the numerator equal to 0. Okay, so we're setting the whole function equal to 0, but practically that means setting the numerator equal to 0. So if we set that numerator equal to 0, we'll solve for x and get x equals 3. So we have an x-intercept at x equals 3. Okay, let's find our y-intercept. The y-intercept occurs when we plug 0 in for x. So if we plug 0 in for x, we'll have 2 times 0 minus 6 over 0 plus 3. Gives us negative 6 over 3. Negative 6 divided by 3 is negative 2. So we have a y-intercept at y equals negative 2. All right, intercepts and asymptotes. Here are our x and y intercepts. Now we'll find our asymptotes. Starting with the vertical asymptote. We find vertical asymptotes using the rules that we talked about in the previous videos. To find the vertical asymptote, we're going to set the denominator equal to 0. So we want to take that denominator, x plus 3, set it equal to 0, and we see that if we solve for x here, we're going to get x equals negative 3. So x equals negative 3 is our vertical asymptote. So a quick point of clarification here. Our x-intercept, x equals 3, is a point. So is our y-intercept. Our asymptotes are lines. So this is actually a line. The vertical line, whose equation is x equals negative 3, is a vertical asymptote for this graph. And then we have to find our horizontal asymptote. So the horizontal asymptote, I can't really write it shortly here, but use the rules, or we can say the rules were all based on comparing n and m, where n and m are the degrees of the numerator and denominator. So n is the degree of the numerator, m is the degree of the denominator. When the degree of the numerator is bigger, we have no horizontal asymptote when the degree of the numerator is smaller. The horizontal asymptote is y equals 0. And when the degree of the numerator and the denominator are equal, the horizontal asymptote is the ratio of the leading coefficients. So in this case, the degree of our numerator is 1, right? It's the highest power of x. The degree of our our denominator is also 1, the highest power of x. So in this case, we have n is equal to m. And when n is equal to m, as I just mentioned, our horizontal asymptote is the ratio y equals to the ratio of the leading coefficients. So the leading coefficient here in the numerator is 2, and in the denominator is 1. So our horizontal asymptote is 2 over 1, or y equals 2. Okay, and that also, again, is a line. These are horizontal asymptotes or vertical asymptotes. These are lines at x equals -3 and y equals 2. So now we're ready to go ahead and plot all of these values here. These are actual points on the function, the intercepts. The asymptotes are lines that break up the function, so they're not actually on the function. So I'm making that distinction because I'm going to use my colors here to try to help out. I'm going to do the asymptotes in a different color than the actual function. So I'll draw the asymptotes here first. We have an asymptote at x equals -3, and we should just draw asymptotes as nice dashed vertical lines, horizontal lines, but dashed lines wherever they go. They're not actually part of the function, they just direct the behavior of the function. So there's our vertical asymptote at x equals -3. We have a horizontal asymptote at y equals 2. So here's y equals 2. So again, we'll do a nice dashed line, this time horizontally for the horizontal asymptote. So there are our asymptotes. Now we want to draw the intercepts, and I'm going to switch to a different color because I'll draw the actual function, the actual curve in blue. And so these are actual points on the graph, our x and y intercept. So x equals 3 is the x-intercept. So at x equals 3, I have a point on the graph. The y-intercept is y equals -2. So at y equals -2, I have a point on the graph. And now I'm ready to sketch the curve, okay? So remember, we said the parent graph looks something like this. And as you do a few of these, you'll start to get the hang of it. But by and large, our curve chunks are going to alternate on opposite sides of the x-axis. So if we look at this corner of the graph right here, on the bottom right of these asymptotes, these two blue dots have to be on the curve. And so if we were just connecting the dots here, they would connect like that. And then as you go to the right, it's going to go up, but it can't go past that horizontal asymptote. So it's bounded above by that horizontal asymptote. As you come to the left, it would keep going down, but again, it's going to get blocked by this asymptote, so it's going to go downward forever and get directed toward -infinity by the vertical asymptote. So when you have the dots here, you can sort of use the asymptotes to direct the curve. Okay, if you have any uncertainty, plug in x equals 1 to the function and see what you get. Plug in x equals 5 into the function and see what you get. And you can draw more and more points, and you'll get more and more of the curve drawn out as you plug in more and more points. So that's what step 5 is plot extra points as necessary. Whatever extra values you want to plug in to make sure you know what's going on, that's what you should do. So for example, over on the left side of the graph, once we get past -3 to the left, we don't really know what's going on over here. So let's see what's going on. If we plug in -4, then we'll be able to figure out what the y value is at -4. So this would be doing step 5, is plotting extra points as necessary. If I plug in -4, I get 2 times -4 minus 6 over -4 plus 3. That's -8 minus 6 is -14. 4 plus 3 is -1, so I get positive 14. So that means I have a point -4, 14 on the graph. It's a little bit strange here, but what we see is at -4, my y coordinate would be all the way up here at positive 14. Okay, and we're just drawing a sketch, so we're not going to go ahead, we're not going to be that accurate. What we realize here is that it's going to be above the horizontal asymptote. Okay, when x is -4, y is going to be some value above the horizontal asymptote. So really we can just draw it anywhere over here, but we know that this whole curve piece is going to be above the horizontal asymptote. Again, it's a sketch, so no, a lot of these points are probably a little bit off, or no, not all of these points are perfectly accurate. But being a sketch, what we're really interested in is kind of just generally where is the curve chunk and how does it relate to the asymptotes, and that's all we're looking for. So this blue function, this function here, the blue curve, is the function f of x. These two pieces of curve are the single graph of this function f of x. And again, if you want to plug in more points, more values for x, you can find more points to get it more and more precise. But really, we know that it's going to follow this behavior pattern here where the curves alternate on opposite sides of the horizontal asymptotes. So once we have this bottom right curve, we could go ahead and just plot this top left curve knowing it has to be on the opposite side of the horizontal asymptote. All right, so there's our first example of graphing a rational function. We'll do a couple more examples in this section, and you'll get your chance to practice on the homework.